what if you're not human? Let's dive into the fascinating world of science fiction, or as it's more commonly known, sci-fi. This genre isn't just about spaceships and robots, it's a playground for the imagination and a mirror reflecting our societal issues and technological dreams. So what exactly is science fiction? Let's break it down. First up, the scientific basis. Sci-fi is stitched together with threads of real or speculative science. It explores what might happen if certain scientific principles were pushed to their limits. Think time travel, interstellar journeys, or even genetic modifications. Now the heart of sci-fi imagination. Authors pose intriguing what-if questions. What if gravity could be manipulated? What if Mars became our second home? These questions challenge our understanding and extend the boundaries of possibility. But sci-fi isn't just about the future tech. It's also a lens through which we view our current world. Through stories of dystopias or utopias, authors like George Orwell and Margaret Atwood comment on politics, ethics, and human behavior. It's compelling how a story set in a distant future can reflect on our present conditions. And what sets sci-fi apart from fantasy? While both genres take us to worlds beyond our imagination, sci-fi remains anchored in science, making it plausible, while fantasy delves into magic and the mythical, the true magic of sci-fi, its ability to turn fiction into reality. Many of the technologies we use today, like space travel and virtual reality, were once mere figments of sci-fi imagination. It shows how visionary ideas can leap from the pages of a novel into our everyday lives. So next time you pick up a sci-fi book or watch a sci-fi movie, remember you're not just looking at fanciful ideas, but potentially previewing the future of humanity. One of them might just be the blueprint of tomorrow. The concept of time travel has fascinated humanity for centuries, and it continues to captivate our imaginations. Let's explore what physics has to say about this intriguing topic. Albert Einstein's theories of relativity provide the foundation for understanding time travel. Here are the key points. Special theory of relativity. According to this theory, the flow of time isn't constant. It varies depending on your relative motion. As you travel faster, time passes more slowly for you. However, this effect becomes significant only when approaching speeds close to that of light. This phenomenon is responsible for the famous twin paradox. Imagine one identical twin becomes an astronaut and travels at high speeds in space, while the other twin remains on Earth. The astronaut twin will age more slowly due to time dilation. General theory of relativity. Gravity also affects the passage of time. The stronger the gravitational field, the slower time moves. For instance, near a massive object like a black hole, time passes more slowly. This effect has been experimentally verified, albeit not at extreme scales like black holes. Traveling to the future. Traveling into the future is theoretically achievable, although it might not involve DeLorean cars or blue police boxes. Here's how. Suppose you embark on a journey at relativistic speeds, close to the speed of light. As you accelerate, time dilation occurs. When you return to Earth, you'll find that less time has passed for you than for those who remained behind. Essentially, you've jumped into the future. The challenge of traveling to the past. Now, let's address the more tantalizing question. Can we travel into the past? Unfortunately, this is where things get tricky. Paradoxes and causality. Going back in time introduces paradoxes. For instance, the classic grandfather paradox arises. If you travel to the past and prevent your grandfather from meeting your grandmother, would you still exist to make that trip? Resolving such paradoxes requires complex solutions like multiple timelines or parallel universes, which remain speculative. Energy requirements. Even if we ignore paradoxes, building a time machine would demand vast amounts of energy. Theoretical concepts like wormholes or cosmic strings might allow time travel, but creating and stabilizing them would be beyond our current technological capabilities. Laws of physics. Some argue that time travel violates fundamental laws, such as the second law of thermodynamics or relativity. While these arguments aren't definitive, they highlight the challenges. So, while the allure of time travel is undeniable, the scientific hurdles are immense. Yet who knows what future advancements might bring? The dream of time travel keeps pushing the boundaries of our understanding, much like science fiction itself. Could black holes be time machines? A black hole is an incredibly massive object formed when a dying star collapses in itself. These celestial behemoths possess gravitational fields so intense that even light cannot escape their grasp. Here's how they create a natural time machine event horizon. As matter collapses into a black hole, it creates a gravitational well, a kind of valley in space. The sides of this valley become steeper as you approach the black hole. The point at which it becomes so steep that light cannot escape is called the event horizon. Beyond the event horizon, the gravitational pull is overwhelming, trapping everything, including light, inside. Time dilation. Albert Einstein's general theory of relativity tells us that matter and energy bend and stretch space. Consequently, time also stretches. When you're near a massive object like a black hole, your experience of time changes. Clocks near a black hole tick much more slowly compared to those on Earth. Imagine spending 1 year near a black hole. Back on Earth, 80 years would have passed. This phenomenon was vividly portrayed in the movie Interstellar, bending time back on itself. Now here's where it gets fascinating. A black hole bends time so profoundly that it can wrap back on itself. Picture taking a sheet of paper and joining its two ends to form a loop. That's analogous to what a black hole does to time. This creates a natural time machine, a gateway to both the past and the future. The catch: surviving the journey. Before we get too excited about time-traveling adventures, there's a catch. Presently, we lack spacecraft capable of approaching a black hole safely. Even if we did, attempting to travel into the past using a black hole might be perilous. So while black holes tantalize us with their time-bending properties, practical time travel remains a distant dream, but who knows what discoveries await us beyond the event horizon. What happens at the singularity of a black hole? At the heart of a black hole lies a gravitational singularity, a mind-boggling region where the laws of physics break down and our understanding of space and time reaches its limits. Let's explore this cosmic enigma. What is a gravitational singularity? A gravitational singularity is a point within a black hole where gravity becomes so intense that space-time itself undergoes a catastrophic breakdown. At this point, density and gravity become infinite, and the fabric of space-time curves infinitely. The usual rules of physics cease to apply, and we enter a realm of profound mystery, the nature of the singularity. Imagine compressing an enormous mass into an infinitely small space. That's precisely what happens at the singularity. The singularity is often depicted as a one-dimensional point, a mathematical abstraction where matter is crushed to infinite density. Physicists debate whether the singularity is a physical structure or merely a mathematical concept. We don't yet know for sure. Inside a black hole, as an object collapses beyond a critical point, known as the Schwarzschild radius, it forms a black hole. Within the black hole, an event horizon surrounds the singularity. The event horizon is the boundary beyond which nothing can escape, not even light. The singularity itself lies hidden beneath this event horizon, shrouded in mystery. Ring singularity in rotating black holes. In non-rotating black holes, Schwarzschild black holes, the singularity is a point. However, in rotating black holes, Kerr black holes, the singularity takes the form of a ring, a circular line rather than a single point. These rotating black holes exhibit fascinating properties due to their ring-shaped singularities. In summary, the singularity represents the ultimate frontier of our understanding, a place where matter is crushed to an infinitely tiny point, and the usual rules of time and space break down.